Hello all and welcome to this final lecture on matrix where we are going to learn about orthogonal matrices. And before we get started with this topic, let's quickly cover the highlights of an orthogonal vector. So in case you have skipped this lecture, I will quickly do a recap. So A and B are said to be orthogonal vectors if transpose of A when multiplied with B, it will give you 0 as an output. So as we can see, these two vectors, vector I and j, if I take a transpose of this vector I, then it will be 1 and 0. And similarly, if I multiply it with this vector j, which is 0 and 1, then you can try it by yourself manually or on Python, you will get 0 as an output. Next thing is that both should be at 90-degree angle to each other. And as we can see here in this figure, both these vectors, vector I and vector j, are exactly at 90 degree to each other, and an n-dimensional space can have max to max n mutually orthogonal vectors. Now what does that mean? The figure that we have over here, it is showing a two-dimensional space which is x and y, and since it is a two-dimensional space, the maximum number of orthogonal vectors that can exist here is 2, which is I and j, and it is impossible to have more than two orthogonal vectors within this two-dimensional space. Even if you try to draw one, then after taking the transpose for that vector, if you multiply it with the other one, you will not get 0 as an output, and this is a condition which has to be satisfied in case of an orthogonal vector. And the last one is that orthogonal vector with unit norm are called orthonormal vectors. And in this figure, we are actually showing the example of an orthonormal vector, because when you consider the norm of these two vectors I and j, then you will get a unit norm. So in case you are not familiar with the concept of norm as well, then we have a dedicated lecture on norms that you will find within this playlist only. Okay, so I hope that now you have some idea on the basics of an orthogonal vector. So now let's move back to the topic of orthogonal matrices. Okay, so the first point says that an orthogonal matrix will be formed by all orthonormal vectors as its rows or columns. Now what does that mean? As we have seen in the explanation of the orthogonal vectors, we had two vectors, vector I, which was 1 and 0, and we had vector j, which was 0 and 1. So if we have a orthogonal matrix A, then it will be formed by the orthonormal vectors like this, I as a row and then j as a row, and this matrix can be considered as an orthogonal matrix. Another thing, that when we take the transpose of this orthogonal matrix and we multiply it by the original matrix, or if we do a vice versa, then it will always result to an identity matrix. So this is a property of an orthogonal matrix, and since A dot A transpose is equals to this identity matrix, if we bring this A transpose to the other side, then it becomes A inverse dot identity matrix. And as we have learned previously in the properties of an identity matrix, whenever it is multiplied by any tensor, it results to the tensor itself, which means the transpose of an orthogonal matrix will be equals to the inverse of that orthogonal matrix. So that's another property of it, and because of this, it becomes computationally efficient to calculate the multiplication or inversion. And that is it for today's lecture, and also it was the last lecture on the matrix topic. Going forward, we are going to learn super important topics like eigenvectors and eigenvalues, which is extremely important if you want to fundamentally understand the concepts of principal component analysis in machine learning, which is again a frequently asked topic in the interviews. So just stick to the playlist and keep on supporting the channel, and I will see you in the next lecture.